Jananing Sharadang Deving Ramakrishnam Jagatgurum Pada Padmitayo Sritva Pranamami Muhud Muhu. So I welcome you all to this meeting. It is just not a memorial meeting. It's just an occasion to pay our obeisance and homage to a young boy, I should say, a second or third year student of Newcastle Medical College, University, who left us untimely following a very untoward incident. His parents, Dapati and R.P. Singh, Dr. R.P. Sengupta, they want to celebrate or remember him through humanitarian activities, and thenceforth Dr. Sengupta really plunged headlong into the service of humanity. You know, he has created a neurology hospital, INK, Institute of Neurological Sciences, Calcutta, or Kolkata, here. He stays 15 days in London and 15 days in Calcutta. And this building, those who have seen it, it is really the memorial of that Santanu Sengupta. Psychological memorial, you can say, though not physical. He has inspired him, Professor Sengupta, a world-famous neurologist, neuroscientist, neurodoctor. So I'm not going to read out that great life which was cut short by the ill fate of ours, I should say. He used to carry a photograph of Sri Ramakrishna and little book, My Master, by Swami Vivekananda, in his pocket. He never told a lie, even if it meant escaping from trouble. In spite of his very short life, he gave much joy to his family and to everyone around him, and to us, the Calcutta people also, in a way. Today's lecture, in his name, will be delivered by Professor Mahananda Dasgupta in English, especially in English, but I will request her to speak in Bengali by way of making just a summary for 5 or 6 minutes for our listeners who are not so much aplomb or efficient in understanding your English, because you have been living outside India for long. You had your education not here in Bengal. You can speak Bengali, can read somehow Bengali, that much. She is the scientific director of Heavy Ion Accelerators, Australian National University. Nuclear physicist also, known internationally for research in accelerator-based nuclear reactions, including fusion and fission. So I am going to speak about the speaker more than the boy, for obvious reason. In her research career, Professor, she is also Sengupta. Mahananda had led paradigm-changing nuclear fusion research, recognized by the Fellowship of the Australian Academy of Science in the year 2011 and Fellowship of the American Physical Society in year 2019. She was awarded the Queen Elizabeth II Fellowship in 1998, and in 2006 was awarded the PAS medal, and also Pause medal, PAWSUI, Pause or Pause? Pause medal, and also is the joint winner of the 2023 the BOAS medal, BOAS, for excellence in research. Subject mostly unknown to us and maybe unknowable even after his speech is made. Speeding nuclei, enabling foundational science to societal applications. So the second part may be more easily understandable for us if she can come to our help the way I just requested her. Speeding nuclei, enabling foundational science to societal applications. So I request the speaker to start, and I thank you all. Especially I express my gratitude to Professor Sengupta, Dr. Sengupta, Advi Sengupta. Thank you.
ঠিক আছে। আমি প্রথমে জানাতে চাই প্রণাম ঠাকুর, শ্রী শ্রীমা আর স্বামীজিকে। শ্রদ্ধেয় সুপর্ণানন্দজিকে আমি জানাতে চাই কৃতজ্ঞতা যে উনি আমার এখানের লেকচার আয়োজন করেছেন। শ্রদ্ধা জানাতে চাই মিস্টার শান্তনু সেনগুপ্তকে, আর কৃতজ্ঞতা জানাতে চাই ওনার ফ্যামিলি যিনি এই লেকচারটার জন্যে দায়ী আর এখানে উপস্থিত। আমি কৃতজ্ঞতা জানাতে চাই আপনাদের সবাইকে যে এই বিকেলবেলা সময় ডিসেম্বরের শেষে এখানে এসেছেন। And I hope to rise up to the challenge that you have put me. So I'll switch over to English as instructed. So it's such an honor and a profoundly humbling experience for me to be standing here in this esteemed organization, an organization with which I was familiar right from the time when I was able to make sense of anything, because of my grandmother, my parents, and my relatives, who were all giving us quotes and examples from the life of Thakur, Sri Srima, and Swami Vivekananda. In that respect, I wish that my parents were here today to see me here. So with that, I will start. I'll talk about speeding nuclei, and as it's clear, like speeding cars, speeding nuclei are going very fast, and how they enable foundational science, progressing foundational science to societal application. Let me start with something. We are all curious. We are deep thinkers, and we are looking towards answers. Answers to our existence, our spirituality, and our physical world that we see around us. And it is the physical world that we see around us that I will address today. And one of the foundational questions which everyone asked right from the ancient times is what makes things around us? And that's something which everyone pondered from long back. 600 BC, Thales thinking that the world originated from water. 450 BC, where matter was thought to be made of 4 elements, and in India, 5, Panchabhuta, which was air, fire, earth, water, and akasha, which is space. 1660s, there was the hypothesis of the fact that the matter was made of tiny elements, and that was the corpuscular theory. And many in the physics audience, those in physics, would realize the name Robert Boyle. 1789, 33 elements, including some strange ones by today's, from our today's understanding, like light and calorific. And finally, to 1869, when the periodic table of elements, which classified the elements in the most scientific way, we know that's due to Mendeleev. So now, today, as a result of all this ancient times ponderance and the experiments that happened since, we know that everything around us is made up of atoms. The water, the sand that we walk, the trees, and us are made up of atoms. And we see that collection in visible light, which is typically 400 to 700 nanometers, which is very small sort of time scale, length scale. But we can't see the atoms because the visible light is not sharp enough or doesn't have high enough resolution to see it. For that, we need to go to an electron microscope. And what is shown here is silicon atoms on a surface, and you can see the individual silicon atoms. That's going down 5,000 times smaller in length scale compared with visible light. We go down deeper. Now, the nucleus of an atom. The nucleus, as the name suggests, is the core of the atom, and it is extremely small. And most of the weight of the atom is inside the nucleus that you see here, the atomic nucleus. What do we mean by most of the weight, and what do we mean by small? This is one of the largest stadiums in Australia, the Melbourne Cricket Ground, where a few days from now, India and Australia will have its cricket match. And so that's why I thought I'll put the Melbourne Cricket Ground here. It's a bit smaller than the Narendra Modi Stadium, but larger than the Salt Lake Stadium. But if the atom was that size of the stadium, then the nucleus of the atom is like the size of a sugar cube put in the center of the stadium. Not just that, 99.97%, that means almost all the weight of the atom, is in that tiny volume. And that's what allowed, in many ways, the nucleus to be discovered by Sir Ernest Rutherford. So you can see, nucleus is very heavy. It's tiny. It's 10 to the power minus 14 meters, extremely tiny. Even I, who work with nuclei all the time, can't imagine. So I thought I'll give another analogy. If you line up 5 billion nuclei next to each other, it'll come up to the thickness of human hair. That's how tiny it is. And in that tiny volume is packed all the protons which are positively charged and contain all the mass of the atom. To investigate such tiny scales, even the most powerful electron microscope can't come close. And we need particle accelerators or speeding nuclei to see the heart of the matter. And that's why we need accelerators, and that's why I work in an accelerator lab. This is one of the earliest of particle accelerators, which was used to study nuclear reactions, which is what I do. And this was made by Sir Mark Oliphant in Cavendish Lab. There is a source of hydrogen at the top, 300,000 volts, to accelerate that hydrogen towards something and shoot it at a target, as we call it, to see what happens. What did they see? They fired deuteron, which is a heavy hydrogen, on another one. And what they saw is some other particles emerge. A proton, which is one of the constituents of nucleus, and triton, which is another heavier form of hydrogen with one proton and 2 neutrons. Here neutrons are blue, protons are red. Not their actual color, that's our imagination. What they saw was the 2 charged particles that emerged. They had much larger energies than what was introduced. Let's think of, to understand that, think of a scale which can measure nuclear masses, a specialized scale. It meant that the things we start with are heavier than the things we ended up with. And they pondered, how is that possible? And that's possible because of the famous relationship, Einstein's energy and mass equivalence. That meant that there was some mass lost which got converted to energy, and if we added that energy back, we would balance. And that's what was happening. So we now have energy in huge quantities, which powers the sun, which powers the stars. And that was the outcome of the experiment from the accelerator, which was designed to understand the heart of the matter. same accelerator was then used. This is a cloud chamber photograph from that time. A lithium target, proton beam, which is hydrogen beam, coming down. And what they saw was 2 alpha particles, which are helium. The helium gas balloon that we fill in when the balloons go up, it's that helium. For the first time, we had created, or humankind rather, had created another different element from what you started with. We started with lithium and a hydrogen, and we end up with helium. Different element. This is unlike any chemical reaction where the constituents remain the same. If you burn petrol, you will end up with carbon and hydrogen and oxygen. But in a nuclear reaction, you are changing the element that you started with. Here are they demonstrating what they found. And now see, they are making these amazing discoveries and taking it to the people with the accelerator they had made to demonstrate what they had seen. I would like to focus on these 2 individuals. Sir Ernest Rutherford on the right, on the left, Sir Mark Oliphant. Rutherford, the discoverer of the nucleus. Sir Mark Oliphant made the accelerator. He was the founding director of our research school. Now they are taking the science to the masses with the accelerator in the foreground here. Modern day accelerators are not that small, not tabletop. One of them is here, 10-story high. It's a 14 million volts. You remember, Sir Mark Oliphant's accelerator was 300,000 volts. We have gone to 14 million volt. It's an accelerator in Bombay. And one of my favorite ones, because that's where I did my PhD. I was the first student out of that accelerator. And one of my supervisors, Dr. Amit Roy, is here today, and it's a particular privilege for me to be speaking in front of him. And this, the experiments that we did together was profoundly exciting, and one which encouraged me to a path towards nuclear physics. Tata Institute of Fundamental Research was started by Homi Jahangir Baba, who is the person in the center, known as the father of nuclear energy, atomic energy in India. On his left, as you would recognize, is Sir Mark Oliphant, now a bit older, and this is the time, this was a photograph taken in Australia. And it's interesting, I found, that the person in the center started the institute where I did my PhD, the person on the left where I did most of my post-PhD work. So let's start our story about at the very beginning. How nuclear fusion made elements, and elements in the cosmos that we see all around us. For that, I have to go back to the origins of the universe 14 billion years ago. It's now understood that we started with a Big Bang, hot, dense matter expanding, and as the matter cooled, in the first few minutes after the start, things begin to cool down, nucleation starts happening. That means now nuclei are being formed in a process called nucleosynthesis. It's a very simple universe with just hydrogen, helium, and very tiny amounts of lithium. That's all we had at the very beginning. And as you will see now, this is the periodic table of elements that I'm showing you. It doesn't show the isotopes, which determines the nuclear properties, and that adds another dimension to the periodic table. Fortunately, we go 200 million years later. Now, fusion is happening deep inside the core of the stars. Energy, you remember the scales, and enormous energy being given out, energy being generated, being emitted by the stars and radiated out. And this powerhouse of the stars and the sun are nuclear reactions. And what kind of nuclear reactions that are taking place depends on the mass of the stars, how far down in their age they are. And in this beautiful, shall we call it, dance of nuclear reactions and gravity, stars are born and die. And all the elements are spread around and come on Earth, and as you will see later, are detected as well in very minute quantities, again, for very, very special nuclei. But that's why we are all made up of stardust. So hydrogen fusing to have helium, nuclei fusing to form carbon fusing to form oxygen, and so on. And so it continues until we form iron. And then this process stops. And the reason is, when you weigh up on that scale, if you remember, anything which is fusing with iron now costs us energy. Therefore, they cannot anymore power the stars, because you need to give it energy to go beyond iron. Doesn't mean it doesn't happen. It happens in more energetic environments, like the supernova. So we definitely know one of the places where heavier nuclei are made is supernova explosions. Now, how do we know that? I'll just come to that. It's very interesting that all the heavier elements which are being made are being dispersed through all these explosions. It is still a very, very active field of research as to where elements beyond gold are made. It is being researched here in India and all around the world, including in my lab. So an extremely profound field of research. So what happens is, as I said, in a supernova explosion, elements are distributed around. And this is the Crab Nebula, very wide, 11 light years. The ashes, this contains the ashes of a supernova, which happened in 1054. It's getting this, because remember, it started with the explosion, it's bigger, and it is getting bigger at 1500 kilometers per second. But how do we know, you might ask, that the heavier elements are made in supernova? We know because, where is it? Okay. So, it makes heavier elements, and some of them are radioactive. That means they are not stable, they don't live forever, they decay away. So something like iron 60 it's a half-life of 2.6 million years. So even if it was formed, and I'm sure it was formed in the beginning, on Earth it has decayed away because the Earth has lived longer, much longer than 2.6 million years. So if there was a supernova, recent supernova, where iron-60 is formed and it has propagated through the universe, then we should be able to detect it. And any signature of iron-60 now means there was a nearby supernova at least a few 2.6 million years ago. So the iron-60, which is a nucleus, which is radioactive, from the supernova, we are bathing in it as the Earth moves through that. It sinks, for example, to the bottom of the ocean and gets deposited in sediments and crusts at the bottom of the ocean. Here's a crust from the deep ocean floor, and you can see, just like tree rings, sediments which have formed, except for a few years or few tens of years, we are looking at million-year time scales. We are really going back in time. This is when Accelerator in Canberra comes in. This is the lab where I work, or I have worked for the last 32 years. If I take a slice of that tower that you saw, this is what you will see to scale. There's 15 million volts at this center. Compare that with the start, 300,000 volts that enabled us to discover fusion. 15 million volts. You start, and at that point, it's it's like a big cloud you can spark. So it has to be held in a special vessel, and that's where all the accelerator technology comes in. How to sustain 15 million volts steadily as the experiments happen. So what we do, we add an electron to the atom. Atom is neutral. So when we add an electron, it becomes negatively charged. Now it sees a positive 15 million volts. It gets attracted towards it. At that point, what we do is we put something called a stripper foil, which is thin foil, and take away all the electrons. When we take away all the electrons, it becomes positively charged atom. And when it's positively charged, it's in a positive potential. Ground potential is there, so it pushes it away. And that's how the acceleration happens. And by this time, you can be going up to 30,000 kilometers per second. That's what is speeding. So we come in, we pull the atom towards the center and push it away. So it's the electrostatic potential which is causing the acceleration. There are other accelerators of different kinds, but this is one I would be talking about. And then once we get the speeding nuclei coming down, then we use a magnet to bend it and send it to all the different experimental halls where different types of experiments are set up. This is where iron-60 is being measured. This is the only lab in the world where iron-60 can be measured to the precision that is required to understand the origins of supernova explosions and getting iron-60, particularly measuring iron-60. About measuring iron-60 is where we specialize, one of the areas we specialize. And that is what has enabled, this precision is what has enabled us to understand how iron-60 was formed. So this is an example the time period in millions of years, iron 60 rate on the vertical axis, the stars show the peak, the iron 60 atoms being measured, and we can see that the Earth passed through supernova debris about 2 to 3 million years ago. That was the closest supernova to Earth in the past. And just to show, science is always done in a team environment, I have put in some of the people who have been involved in this measurement. That is good. So we understand that all the elements are being made in the cosmos, in the stars. But how do we discover new elements? And how do we know the limits of our existence in terms of the number of elements? This is what brings us to the question of what I call artificial elements. That means they are not normally found on Earth. If you go and dig for it, you can't dig for artificial elements, but they were present. They have decayed away. But they were made, and now we make them on Earth using accelerators. For example, there are particular exceptions. You see technetium here, right in the middle of periodic table. Not found on Earth, but used in 75% of the nuclear medicine would involve technetium-99. Used for scanning heart muscles, liver, brain, huge range of applications of technetium. First produced because of nuclear reactions, now produce again nuclear reactions, but a byproduct of the nuclear reactors. And that has, I'm sure, has touched huge number of lives. Then you see the other elements, you see, are mostly heavier than uranium. Uranium is the last kind of heaviest element you can dig from Earth and sell in quantities, not the others. The rest are all heavier. I would like to highlight another one of those elements, plutonium. Again, an artificial element, but it can be used for detective work, just like technetium can be used for detective work by the doctors, detecting things, how our body, how the cancerous cell, or how the functionality is happening. You can use plutonium and many others. I'll just use the example of plutonium to understand how our Earth functions. I take one of the iconic examples of Australia, the Great Barrier Reef. It's in the northern part of Australia, one of the very beautiful sites, natural sites. But there was a problem. There was soil erosion happening and coming into the barrier reef. And that was affecting all the corals and animals, creatures that lived there. The question was, where was the soil coming from? And that part, so now I've sort of zoomed into that part. You can see the map of Australia there, zoomed in version. It's an intensive sugar cane farming region. So everyone blamed the sugarcane farmers. And what our lab was able to do was look at soil samples And by measuring plutonium-239, which is a particular isotope which is decays away, they could figure out what was happening. But it's not that easy, because you have to detect one atom in 10 to the power 10 atoms of other plutonium. Going back to the Melbourne cricket ground, you remember how big it was. It is like hiding 6 grains of sugar in Melbourne cricket ground, or maybe 4 in Narendra Modi Stadium, and filling the stadium to the brim with salt. The accelerator will find that in 15 minutes. That's the level of sensitivity that you can get with an accelerator. It's in an area called accelerator mass spectrometry. And that was used to show that the soil is originating mainly from collapsing riverbanks and not directly as a result of the farming practices, which meant that we had to, all the results affected how the government policy was being formed. So, coming back to our artificial elements, we will go to fusion, because the discovery of elements is very strongly linked with nuclear fusion. And you can see how the understanding of fusion has proceeded. In 1932, when I showed you that accelerator which Sir Mark Oliphant had made, they showed that mass differences lead to release of energy. This is what was powering the stars. In 1970s, as accelerators became more powerful, that means higher energies could be obtained, people were able to fuse light elements with heavier targets and discover new elements. In 1990s, when I started my career, more nuanced detectors were available. We could make precision measurements. Accelerators were there with high enough intensity of particles coming out, which meant we now understood how quantum nature of nuclei affected their behavior. And it was understood that the nuclei, when they approach each other, go into a quantum superposition, which is highlighted in the normal press, like popular press, as Schrodinger's cat who can be dead or alive. So it is the same kind of thing, that the nuclei come into superposition of different states, their quantum states, and that has a profound effect on fusion. You can have a change in a factor of 1,000 in the probability of fusion. As I said, fusion is strongly, and the understanding of nuclear reaction was strongly linked with discovery of elements. This shows the number of discovered elements as a function of year. The elements known to humanity, we start at 20 elements only, 1750, up to 118 elements that we have today. And with each, you see, it's not a linear curve. It has little steps. And every time there are steps, there are new things coming in accelerator or understanding, and so on. It's the technology, the science, the detection ability, our understanding of how to make the new elements, all are coming together to get us these little jumps that you see. So rare earth and actinides being discovered there, fusion of light ions gave rise to that next jump. As the accelerators became more powerful, bigger nuclei could be, heavier nuclei could be accelerated, which meant there was another little jump which came in. And as we understood the quantum nature of nuclei, we found that calcium-48 is a very special nuclei. We still don't understand why, but that is what led, beams of calcium-48 is what let us discover the heaviest of elements that we now know. Now, soon, the last element was discovered, new element, was discovered in 2009. Soon, this will be the longest period in our humankind, or so far we know, since 1750, that no new element has been discovered. And as I said, every time there was a jump, that meant there was a new science, a new technique, or new something which is coming in. So the question is, why is it so difficult now that we haven't had a new element made? And to study that, we have one of the best fission. Ognason. And very interesting, there are only 2 elements which were named after people who were alive when the element was named after them. Seaborgium, who by the way discovered technetium, but seaborgium, and Ognason. Ognason is the one, Ognasian is the person from Russia. He found out that if you use calcium-48 beams, that is what will lead you to heavier elements. So, continuing on, so we now want to know, why is it so difficult? So we study a process which prevents the formation, which prevents fusion, or the formation of heavy elements, in process called quasi-fission or fission. And this is a detector array in Australia made by my colleague, David Hind, which is one of the world's best in measuring fission. And what we find is the measured fusion probability on the vertical axis, product of charges, which means as I go further in, the nuclei are getting bigger and bigger. That means we want to make heavier and heavier elements. That you see that the fusion probability is going down. Theoretical expectation would be right at the top, 1, but it is not 1, it's steadily going down. And why is that? And that's what we now are currently investigating. So we want to look at nuclei which are not fusing. And for that, what we do, okay, so there's something fundamentally we do not understand. So let me now do a very gentle collision, have the energy so low, fusion cannot happen. So what is happening, even when fusion is certainly not happening, but what are the other things which are occurring? So we send that, the beam from the accelerator, the speeding nuclei coming in, that's the target, and we measure the energy of the particle which is coming out, much like what Sir Mark Oliphant did, but in a different and more accurate manner, measure its energy, mass, and charge. And here's a probability, and the change in the kinetic energies, the change in the speeds, if you like. If nothing changed, which is what would be the expectation when things are very far, not much interaction happens, everything should have been dead at 0. That's what would be the expectation. But what we measured is what is shown here. It's somewhat peaked at 0, the expectation, but there's a big tail. And clearly, it's not what we expected. And again, work which is done in our group together with my young colleagues here. What was clear is that there was some energy being lost And that effectively means that the nuclei are, the trajectories are not perfect, they are being perturbed because of this loss in energy. And those who have lost energy are being pushed away, and therefore fusion is likely to be reduced. More than that, also what we observed is that even that far away, the nuclei are changing identities. And what we saw is there are many nucleons being exchanged, and if you plot the minimum distance between the two nuclei, that means 0 is they are almost touching, then we see that the number of nucleides being exchanged, number of nucleides that we see is not just 2, but 30. And so there's a huge complexity in the fusion of heavier nuclei that we do not know. And that's what we are investigating. So what's the future? We see that we have moved from 1932 to 2024, where we understand that fusion of heavy elements is much more complex. We are asking questions like, when do these exchanges happen? How does this impact fusion? How does this irreversibility, which for the people who are in physics, because the nucleus and nuclear collisions are very isolated quantum systems, that means there should not be any loss of kinetic energy going into heat. It's purely as a quantum system. But that is what we are seeing, and how does that take place? How can we understand the loss of energy? And will we ever discover a new element? And if so, how will we do it? And I would believe that we will discover a new element. In fact, there are experiments happening right now. But and it will be another jump in our understanding. As a final thing, I would like to show accelerator being planned in Australia. There are accelerators like this all around the world, but a new one is being planned in Australia. And that is not a lab. That's a treatment center. And that is going to use proton beams to irradiate cancerous cells, particularly in pediatric cancer, for cancers in brain and neck. So why proton beams? That's because of another Australian, William Bragg. There's something called the Bragg peak. Let me just walk you through. So this axis is the dose. That axis is the depth in tissue. If you use X-ray beams, then that's the green curve. Most of the dose is given at the surface. So if the tumor is deep in, most of the dose is being delivered to the surface, and then some are coming into the tumor. But if you use a proton beam, dose is shown by the red curve. The amount of dose in the surface is less, and the peak, which is called the Bragg peak after William Bragg, is where the particle stops. So all the energy is deposited in one big hit there. That means there is less damage to the surrounding tissues, and that's why it is used preferably for pediatric cancer. And that is a very practical use of ion beams. And you might say, okay, have an accelerator, shoot the beam through, and that's it. Why do you need to know nuclear reactions? That's because you start with a 200 MeV, which is very high energy proton beam, and it undergoes nuclear reaction as it is going through our bodies. By the way, the same thing is happening when satellites go up into space. There's radiation, there are nuclear reactions happening, and that's another area which there's work happening all around the world where people are testing satellite components. So the proton beam comes in and has to stop. But all the way, there are nuclear reactions happening. And all these things that you see here written in English, but it is technical, so which means that there are all these theories which are going behind all the reactions that are taking place, and there are nuclear models or reaction models which are developed, and that's all integrating quantum nature of nuclei with how nuclear reactions take place. So in order to plan a dose and plan a treatment regime, there is behind the works, there are these models which are taking place, which are being put into action to calculate what will be the final thing which will be delivered, what will be the different nuclear reactions which will take place. So with that, I think I will end. And with the summary being that we have a lot to look forward to. Now, you asked me to give something, and no, you're okay? You think I've risen up to the challenge? So I think I'll end here then. Yeah.
Doctors, you have talked to the doctors.
One present.
Only one. But you have some good hospitals over here.
Yeah, we can, maybe next visit I can only talk about that. Yeah.
This cancer patient recently.
Thank you.
So we have no word to thank you.
Oh, thank you very much.
I bowed on my head.
Thank you so much. Thank you.